So finally, we're going to get our solution to the optimization problem. The extra credit optimization problem, which it says consider the part of the parabola y equals 1 minus x squared from x equals -1 to x equals 1. This curve fits snugly inside an isosceles triangle with its base on the x-axis and one vertex on the y-axis. What is the smallest possible area of this triangle? And the answer is that minimum area, which I'm going to call a min here, is 8 times the square root of 3 over 9. Okay, so first off, one thing, so I've dropped a bunch of hints about how to go about doing this thing. One of them, I said, I think as soon as I assigned this, I said, don't worry about this half, okay? And indeed, that's what you kind of want to do in general with a problem like this. If you have symmetry, use it to your advantage. Otherwise, I mean, you could do the whole thing. It's not going to be that hard. Then, you know, here, obviously, this part of the triangle is a line. This is not the same line as this line, and so you're just making your life more difficult if you're dealing with two lines as opposed to one line. So what I suggest we do is just look at this side and say, and first off, notice that this total area that we're trying to find, the area of this triangle, like what we could do is just say, okay, if we have, let's call this big A, the area of the whole thing. If we say, you know, if we find this area right here, say little a, we could say then big A is just 2 times whatever little a is. So we'll get a formula for this area, and then we just, as long as we remember to multiply it by 2, then we'll have the whole area. And again, that's by symmetry. That should be obvious, okay? So in order to do this, to forget this side, I'm going to redraw this thing and actually do a better job here. So I'm just looking at the right-hand side of this triangle. Okay, we have the parabola here. And I'm going to give the parabola a name instead of y. I'm going to just call it f. F of x is 1 minus x squared. Okay. Now, the whole part about it fitting snugly inside this triangle. Oh, that looks terrible. I'm sorry, I gotta do this again. I'll have to go right in front of it and do it. It's gonna bug me if I don't do that. Okay, so there's the parabola, and we'll say this right here is part of the isosceles triangle, and the fact that it fits snugly inside means that it's a tangent line to that curve. That is, this side of the triangle is a tangent line to that curve, so that means it's going to touch at one and only one point of this parabola. Okay? Now, let's think about this for a second. I've just drawn a mathematical object up on a graph. Let's write down a formula for it. Since it's a line, it has the form y equals mx plus b. There you go. Okay, a couple other points we could look at here. This is 1, right? That's a 0 of this guy. You plug in a 1 into f, you get out a 0, so that's that. Plug in a 0 for x, you get out a 1, so we know that point right there is 1. May or may not help us, who knows? I'm just trying to get as much information as possible. Okay? And so then, now let's think about our steps for doing an optimization problem. First, we want to identify the quantity that we want to optimize. Since area is the quantity we want to optimize, then I need a function. I'm going to call it A. And let's just give this a second here. So first off, the area of a triangle is 1/2 the base times the height, okay? So I'm just getting that up on the board, not sure exactly how I'm going to use that yet, but it's just nice to have it up there. And just looking at this triangle, I could see a couple things already. that the base, because of the way that this is centered here, the base is exactly this length right here. Whatever number that is the same thing as the base. That length from 0 up to B is the base of the triangle. Ditto with this guy. Whatever value that is right there, that's the height of the triangle, so that's H right there. And so, cool thing about this is a line, and these are that's just the x-intercept of that line. That's just the y-intercept of that line. So if I get the x-intercept and the y-intercept, I could get that. But now we have to think about our constraint, right? Because right now, this is a function of two variables, base and height, okay? I would like to drop that down into one variable, but we have to be careful about how we're going to do that. And as I'm looking at this, right, I'm thinking about, this is kind of what goes through my head. I'm going to do it in pictures here. This is what goes through my head is, we have some parabola. And we're going to put a line on it, right? I'm going to take like some straight edge and draw a line on it. There's a bunch of different ways I could do that. If I do it right here, then it goes up like this, goes down like that. If I move it over a little bit, looks like this, goes down like that. If I do it way up here, it goes here and comes out like that, right? And so I'm thinking about this really is the question, is where do I draw this so as to make this resulting triangle have the smallest area? And I've said this before, right? It's pretty clear that the closer I put this dot up here to the top of the parabola, if I did it on exactly the top of the parabola, well, we would have just a straight line going just straight across, so that can't be it. And if I bring it back by a tiny fraction of a fraction of a fraction, well, it's pretty clear that this triangle could be made arbitrarily large. Its area could potentially be as big as you want, right? So already I'm thinking, all right, if I do all my work and everything and I find that if I put it right here, the closer I get to 0, like the bigger the area is going to be. I'm going to use that to check my work here once I finally get a formula for this. So, if you notice, the thing that's being varied here, as the way that I frame this, the thing that's being varied is where does the tangent line actually touch the function f? And I can see that as I vary that position, it changes the area. And so I'm thinking, okay, well now I have a variable, right? I have some value I could plug in here. And it's only one value. I'm going to go ahead and call it x. There's some value, x. If I choose an x, right, somewhere between 0 and 1, obviously, because if you go out past 1, you're doing this, and that's not the triangle that they told you to do. So it's got to be some dot between 0, and as we just said, it can't be 0 because you would just get a flat thing, it wouldn't be a triangle. So it's got to be the fact, like x has got to be bigger than 0. Also has to be less than 1. So that's kind of what's going through my head as I'm looking at all of this, right? And I can see that as I vary x from 0 to 1, that's ultimately what I'm doing here. Now, so the question is, can I get this thing to have one input x and give me out one output area? If that's the case, then I have a as a function of x, area as a function of one variable. I can take the derivative of it, set it equal to 0, and find out where that function has a max or a min, right? So that's kind of the game plan here. Okay. This is what makes this problem so difficult. I'll show you in just a second. There's a few things about it that are difficult, but this is what kept me going through a loop forever and ever and ever. I'm going to do what I call the naive approach. Okay, And not to say that like one is dumb if they do this. I did this over and over and over and over again. But like if you just go through it with, you start off like this. You say, okay, well now I'm just going to go through and just plug and play and see what I could get, right? This is what's going to happen. We're going to run into a problem. And I want you to see this problem that we're going to hit, because there's something to be learned here. Okay, so the idea is I'm going to get A of X now. I'm going to say what I want is an A of X, where I plug in that X, and for any value of X you put here, I want to know the area. Well, here we go, right? So the slope of this, well, okay, coming back now, we have this guy right here. And like I said, we need B and we need H, and we could get that all from the equation of the line, because B is just the x-intercept, H is just the y-intercept. So if I get those in terms of X, I could plug them into here and just plug and play, and I'll be good to go. Okay? One more thing just before I begin. This is 1/2 the base times the height for this, right? And we want this area here is the area of the full thing. So why don't I go ahead and just multiply it by 2 to get the area of the full thing? So this is the area of this half triangle. If we double it, then we get the area of the full triangle, which is the thing that we're looking for. So multiply this by 2, the half kills the 2, and we just have base times height. Okay? Okay, now we're ready to plug. So all of my information, everything I need to find B and to find H is right here. The only problem is I need to know what M is and I need to know what B is. But M is the slope of this function at this point. So I'm going to say, okay, f prime of x is, I take the derivative of 1, goes away. That's a negative. The 2 drops down, and we have an x. Okay? So, at x, f prime, the slope at x, what I get is minus 2x. So I'm going to go ahead and say, okay, that's what my m needs to be there. I'm going to plug it into there. That gives me y equals minus 2x times x plus b. Okay? Now the only other part we need is b, and we should be home free, right? So what I need to do is say, all right, I have one unknown, I need 1 point here to give me. Well, I know its x position, what's its y position? If I knew its output, because this is the only place on the parabola where that line touches, they should have the same output there. So when I plug in an x into f of x, I get the output is 1 minus x squared, right there, right? Because it's on the parabola, so it has the same value there. And so this says, when I plug in an x for here, so I'm going to do that, minus 2x times plugging in my x plus b. What I get out is a 1 minus x squared. Now we're going to solve for b. We get 1 minus x squared equals, that's negative 2x squared plus b. Bring the negative 2 over. So that's plus 2 minus 1, and we get plus x squared equals b. Now, okay, I can plug that into here, and I should have everything I need to know. So y equals negative 2x x plus b plus 1 plus x squared, like that. Okay? Looks good. That should be the equation of the line. Okay? Let's clean this up a little bit. Minus 2x squared, minus 2, so that should be minus 2x squared plus 1 plus x squared. Y equals, I guess we could call that minus 2x squared plus 1x squared is a minus 1x squared, so how about 1 minus x squared? And that's the equation of your line. Is that an equation of a line? That's not an equation of a line. That's your original function. What's going on here? Well, let's say that we didn't notice and we're just plugging and playing. This should be a dead giveaway that you did something wrong. But let's let's say that we didn't notice. Let's just say, okay, all right, now we just need to find the y-intercept and the x-intercept, right? To give me b. So to find b, I set y equal to 0 and solve for x. So I'm going to set y equal to 0 and solve for x. X squared equals 1. Take the square root of both sides. X equals plus or minus 1. But minus shouldn't mess with you too much because, well, we cut off half of this. This is a parabola, right? It should plus and minus. It makes sense. And so you might think, oh, okay, well, ow, we found it. X equals 1. So b would have to be here at 1. Okay, well, let's find the h now. H is what happens when I take my line, it's not a line, and you plug in a 0 for x and find out what the output is, h. So my b should be 1, and my h would be, well, I plug in a 0 for x, and I get y equals 1 minus 0. Wait a minute. Y is what I get when I plug in a 0 for x, and y equals 1. Okay, y equals 1. That should be it. One thing to notice, another thing that should kind of throw you through a loop is that, well, now your x is gone. You're looking for a function of x because you're trying to take the derivative of it, right? That was the whole goal. If I have some relationship, but that's two variables. Base is a variable, height is a variable as you change x. So if we could get it just in terms of x, then we'll get the area at any point, but now the x has disappeared. And this is the only area for this thing, no matter what x is, has to be, well, I guess 1 times 1, the area would be 1 of the whole thing. But what it's saying is that here's your parabola. We know the parabola goes through at 1 and at 1, and it's saying that that's what this is. That's not what we're supposed to do. What's going on here? And so you go through and you try this a bunch of different ways, and you almost inevitably end up back at this point, and you're like, what is going on? And you try it again, and you try it again, and you try it again, and what could possibly be going on? Well, this is what's going on. You called this thing x. You shouldn't call it x. Because these x's, right, this does not change, does it? Like, f of x being 1 minus x squared is this object. This thing, y equals mx plus b, tells you what this is. The x is not the varying thing. The thing we're coming up, we want to come up with a new parameter here. We want to come up, in fact, a new variable here. We're going to rename this thing right here. I suggest that since there's two ways of doing this, either rename this x, and then the thing that you're varying you could call x if you like, but it's going to be easier since we already have this up here to give this thing a new name. And I'm going to call it t. And now x, the 1 minus x squared and the mx plus b, that deals with these two objects just being objects by themselves. They're not changing, right? Well, I mean, this changes as you change t. But for all of that, that's just, well, like, especially with this guy right here, he's not moving, right? We don't want to change the values of this x, though they're already given, right? We know that he lives right here. The thing that we're changing, we want to give a new name. So that's what we're going to do here. We're going to say, okay, the thing that I'm changing, I want to call it something else. I'm going to call it t. And now what I'm looking for, instead of having a function of two variables, b and h, I want a function of one variable, a of t. And now we're going to go through the exact same reasoning as we did just now. The exact same reasoning. And we're going to see what happens now that we've made this slight change. Okay? All right. I need a B, I need a H. I notice that B is the x-intercept of this line. H is the y-intercept of this line. So in order to have an actual line, I need an M and I need a B. M's easy to find because this line is tangent to this curve at the point T. So when I take f prime, I get, again, minus 2x. But now, it's not x that I care about, right? And you can see it changes. When t is 0, well, the slope should be 0. When t is 1, the slope would be negative 2. But now we're going to say, well, what happens at t? What is its slope at t? And so that's going to be f prime of t is negative 2t. So that's my slope right there. So I'm going to take that, plug them into here. Y equals negative 2t x plus b. Okay. Now I need to find little b. Okay, the intercept, which happens to be h right there. But, okay, so the way that we do that with a line is we plug in 0 for x and see what pops out. Oh, I'm sorry, that's b. That's how we find the intercept. But in order to find b here, we need a point that we know is on the line. And we know that when we plug in a t, we get out a, oh, that's going to make our lives a lot better. It's not 1 minus x squared that pops out. T, when we plug it in, we get 1 minus t squared. And so now, okay, let's think about this. Here's this line, and it says when I plug in a t, so I have negative 2t, plug in a t, the thing that pops out is 1 minus t squared. Okay, let's clean this up and get b by itself so we have our intercept. 1 minus t squared is negative 2t squared plus b. Bring this guy over and we get 1 plus t squared equals b. All right? Okay, now at this point, since we already messed up, and if you did it like me like 1,000 times and you kept ending up with this answer for your y-intercept, you might be like, uh-oh, I'm going to go down this same rabbit hole. I must have done something wrong, but let's just have some faith here, okay? Let's plug this back into here. Now we have our equation of the line is negative 2tx. See how nice that is to have a different variable? Now we're not going to end up with that weird stuff that happens. Plus b is 1 plus t squared. Okay. Now let's see what happens. We could obviously find the we know that this is the y-intercept, and so that's h right there. But in general, if this thing isn't a line, the way that you find a y-intercept is you plug in a 0 for x. So that's what I'm going to do. I plug in my 0 for x, and I get that. And I get 1 plus t squared is the height that I'm looking for, right? Did I do that right? Yeah. When you plug in a 0 for x, and you see, it's not t that we're letting go to 0, which is why everything got so crazy a minute ago, right? This is a line. It's dependent on x. It's a function, y equals mx plus b. Now we're kind of going back to this being a function of x, and we're saying, okay then, when this line, which lives right here, and yes, like you could imagine that we've selected some t, boom, there it is. Well, now this thing, now that t is given, this has some slope, like negative 1 or negative 2 or something, right? And we could say, okay, where is its intercept? And that's what we're doing right here. We're saying, what is that intercept right there? Well, when you plug in a 0 for x, that goes away and you get whatever y equals 1 plus t squared must be that height that we were looking for. 1 plus t squared is h. Big H right there, right? Okay, and so now we need to find the x-intercept, which is b. The way we do that is we set y equal to 0 and solve for x. And so I'm going to take this guy here, make his output equal to 0, negative 2t x plus 1 plus t squared. And now I just need to solve for x, because we're finding for what x value does it give me a 0 output, which is where b is. So I'm going to bring this guy over and say 2t times x equals 1 plus t squared. Solving for x gives me x equals 1 plus t squared over 2t. And that is my b right there. There was my h, there was my b. So this was 1 plus t squared over 2t, like that. Okay, and so now the area that I wanted was b times h. I have my b as a function of t, I have my h as a function of t, and so now I could get my area as a function of t. And so base was 1 plus t squared over 2t. Height was just 1 plus t squared. And there you go. That should do it. Now, let's do some checking, because remember what I said. Like, at this point, if you're like me, you worked on this for a very, very, very long time, and you're wary to keep going if something's messed up. So let's do a little bit of checking here. I said, this area function, this output should be the area of this triangle. Actually, because we multiplied by 2, it's the area of the full thing. But it should give me the area for whatever value t I plug in. So there's a couple points I could check. One thing I could just do, like forget about this problem and say we had this parabola, 1 minus x squared, and I want the tangent line right here at 1. I could say the derivative of this is minus 2x, and so if you're here at 1, its slope would be minus 2, right? And if that has a slope of minus 2, then when I go over 1, when I go back 1, I got to go up 2. So this guy should be 2 right there. Now, then the whole thing, right? That whole triangle, it would have a height of 2. It would go from 1 down to negative 1. It would have a base of 2. And so the area would be 1/2 the base, which is 2, times the height, which is 2. 1/2 2 times 2. So the area of that guy should be 2. Now let's see, that happens when t is equal to 1, right? This happens when t is equal to 1 here. So if I plug in a 1 into here, I should get out a 2. Because remember, this is not just the area of this half. This, because we multiplied it by 2 up here, is the area of the whole thing. That's the area of that whole thing. It should be the case that when I plug in a 1 into this function, I get out a 2. Let's check it. 1 plus 1 squared is 2 over 2 times 1 is 2. Times 1 plus 1 squared is 1, so that's 2 over 2, which is 1, times 1 plus 1, which is just 2. So it works there. The other thing we could check is, let's see what happens when t goes down to 0. If I just plug in a 0, oh, this looks good. It should be the case, because we said as t goes to 0, this thing should get arbitrarily large. And one thing, also, knowing that I'm about to take a derivative of this thing, I don't want to take a derivative of that. I don't know about you, but I don't want my function to look like that if I'm about to take a derivative of it. I'd have to deal with a product rule and a quotient rule. No thanks. So what I'm going to do is rewrite this thing as 1 plus t squared times 1 plus t squared all over 2t. First, outer, inner, last, that guy I get first. Outside is t squared. Inside is another t squared, so 2 t squareds. The last is t squared times t squared, which is t to the 4th, all over 2t. Again, I know I'm about to take a derivative, so why keep it like that? Why don't I break this up as 1 over 2t plus 2t squared over 2t plus t to the fourth over 2t, which is 1 over 2t. That's just t. That's just t. This should be 1/2, or how about t cubed over 2? I think that's right. Make sure I haven't messed that up. Yes, that just cancels one of them, 2 stays in the denominator. So I'm going to rewrite this. This is that. So I'm going to rewrite up here. A of t is 1 over 2t plus t cubed over 2. And we could see much more easily now that, yes, indeed, nothing's going to cancel out here. As you try to plug in a 0 in for t, this thing's going to blow up. And that's what we expect. That's what should happen, right? These guys, as t goes to 0, this thing goes to 0. This thing goes to 0. This thing goes to 0, but this thing blows up. And that is what we should expect. That blows up, the area should blow up. So I'm feeling much better about this now. Like, I think we could just plug along because it has the behavior we expect as t goes down to 0. The area should explode. And we know that when we plug in a 1, we just used some geometry here and found that the total area should be 2. Plug in a 1 here, you get a 2. Okay, all right, I feel good about this. So let's plug along. Now, this is an area function. And so we're imagining, okay, we know it blows up as it goes to here, so maybe it does something like this. Who knows what it does? But we're trying to find a minimum value of this function here. What I've just graphed here is at. It doesn't look exactly like this, but it kind of does. And so there's going to be some sweet spot. And again, let's think about our bounds on t. T cannot be 0, so it has to be bigger than 0, and it has to be less than or possibly equal to 1, because it might just be the case that the smallest does indeed come out to be 1, but we've already calculated that and we found that the area would be 2, and the answer in the back of the book tells me it's not that, so yeah, I gotta keep going. So I'm going to imagine here that this thing looks something like this. That there's some value of t somewhere between 0 and 1 where this function has a minimum, and that's the t I'm looking for. How do I find that? Take the derivative, set it equal to 0, because at this place, its derivative has to be 0. Okay? So, all right, let's do that. So, we take the derivative, a prime of t, and we get, okay, that's 1/2 t to the negative 1. Take the derivative of that, the negative 1 jumps down and makes that part negative, and then we get t to the, we have to bring that down one more, that's t to the negative 2, so that's the same thing as negative 1 over 2t squared. So, negative 1 over 2t squared. Take derivative of t, just gives me a 1. Now, take the derivative of t cubed over 2, the 3 jumps down, and then we decrease this by 1 and we get that right there. So that's plus 3t squared over 2. You could write this as negative 1/2 t to the minus 2 plus 1 plus 3/2 t squared, however you want to do it. I don't know, I like it like this. I'm going to go with it like that. Okay, so we've taken the derivative. Now we need to set this thing equal to 0 and solve for t. And this is the other part that's a little bit tricky. If you it's easy to forget what to do in this case, and you look at this and go, yikes, how do I deal with that? There's a few ways we could deal with this, but one thing I want to ask, I've been saying this for 2.5 years, like, there's something in here that's screwing up your life, and if it wasn't there, you'd have a better idea of how to deal with it. it's that you have a variable in the denominator. Let's get it out of there. Now, and there's a couple ways we could deal with this, right? Like we could just multiply everybody through by t squared. We could say, okay, I'm going to multiply both sides here by t squared. Do it over here. It's t squared. That kills that, gives me negative 1 over 2 plus, I guess the t squared comes over. This gives me plus 3t to the 4th over 2 equals 0. That's nice. And we could go further. We could say there's still a denominator. I mean, we could just plug along from here. But again, I see, I have some equation equal to 0, and I have denominators. Let's just get rid of the denominators. It's going to make my life easy. So at the very beginning, I could have just said, let's kill both of those denominators with a 2t squared. But I'm kind of doing it in 2 steps here. It doesn't matter. So the 2 comes over, I get a negative 1. This would be a plus 2t squared. Finally, plus the 2 kills the 2, we get a 3t to the 4th equals 0. And again, we could have plugged along with this, and it would have been fine. Now, what do we do? In fact, I'm going to go rewrite this right here as 3t to the 4th plus 2t squared minus 1 equals 0. This looks familiar. What can we do here? This is what we call it. This has a quadratic form, right? There's no variable that shows up in this one. There's a variable that shows up in this one. And if you square this one, you get that one. So we're going to substitute. All right, we're going to bring in a new variable. Let's call it a. We have a's. How about u? U. Okay? And we're going to say let u equal whatever this guy is right there, is t squared. So that u squared equals t squared squared, or t to the 4th. And now we could get this as 3u squared plus 2u minus 1 equals 0. We'll be able to solve for u, and then we'll know that in the end u is t squared, so we'll take a square root, etc., etc. Okay? Okay, so I'm going to get this out of here. And now, this is, if we had done it with this guy, it wouldn't have been a problem. It's just that our coefficients would have been a little uglier. Because obviously, what we're about to do is plug this into the quadratic formula. Because I can't, I probably could reason out a way of, in fact, we probably could just factor this guy. Yeah, but I don't want to, because I want, I'm just going to plug along, right? Plugging this into the quadratic formula, just a little bit uglier, right? It's just a little bit uglier. And so, this is nice and clean. That's why I took this step, okay? So, okay, quadratic formula. In this case, it's not x, it's u. So, u equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. There we go. Alright, so we get negative 2 plus or minus. This is root 4. Negative negative makes this positive. So that's plus 4 times 3 times 1 is 12. Nice. All over 6. This gives me negative 2 plus or minus. Now 4 plus 12 is 16. Right? Yeah, 16. And root 16 is 4. So that's negative 2 plus or minus 4 all over 6. This gives me, okay. Negative, negative. Negative 2, negative 4 is negative 6 over 6. So that's negative 1. Or negative 2 plus 4 is positive 2 over 6, which is 1/3. So we have 2 possibilities now. Because you might say, oh, it's that, plug it in. No, wait, remember we did this. We gotta do this. U, we just solved for u. We said that u is either negative 1 or positive 1/3. So now, well, let's go back and find out what t has to be. Okay, so if u is t squared, and u is negative 1, then t squared is equal to -1. So t equals plus or minus I. And the last time I checked, I does not live on the positive x-axis. So I think we could get rid of this guy right there. I don't think that's going to make any sense. You plug that in and you're going to get I something. No, the area is not imaginary. It's actual. I shouldn't say real. Okay. Okay, so it must be the case then if u is 1/3, then t squared is 1/3, so that t equals plus or minus 1/√3. That looks right. Yeah. Now, was it plus or minus? Well, the way that we set this up, over here, the t must be a positive number. Like we said, I didn't write it up here, but t, I've said it a bunch of times. T has to be between 0 and 1. And indeed, positive 1/√3, because 1 is less than √3. Well, because 1 is less than 3, 1 is less than √3, and therefore 1 dividing over, you get that guy right there. And so, it's also a positive divided by a positive. It's got to be bigger than 0. So that is the one that we're looking for, right there. Okay? Now, is it a min or a max? At this point, after doing all this work, I'm not even going to bother to check. I really don't feel like taking a second derivative and plugging this stuff in. It just makes sense now that I found that t, the sweet spot here, which I'm going to write as positive 1/√3. As we said, it can't be a max because we know that this thing is unbounded, right? As t gets really, really, really small, this is going to blow up. So it can't be a max. There's only one of them in this setup that work. The only other one that works, it has to be a min. Again, if you don't believe me, I've done this. Take the second derivative, plug him in, and you'll see that yes, it is concave up, up like a cup. So its second derivative is positive if you do that. Oh, why not? Let's just do it. All right, let's just check. Let's be really, really thorough here. Oh, this was a, no, that was a. We found a prime of t was -1, 2 t squared plus 1 plus 3t squared over 2. So it's second derivative. Okay. That's -1/2 t to the -2. So the -2 jumps down. Negative is a positive, so that's 2/2 t to the -3. 2/2 t to the -3 is just 1/t cubed. So that's 1/t cubed. 1 goes away, take the derivative of 1, it's gone. The 2 drops down now over here, kills the 2, and we're left with 3t. Now all we got to do is plug in the positive 1/√3 and make sure that what we get is a positive number, which indeed it is, equals, you took a positive number and cubed it, then you took a positive number and multiplied it, you're adding them together, that's positive. Positive, so that means it's concave up at t equals 1/√3, so concave up looks like a cup, and so it must be a local minimum. So that is where this occurs. This t equals 1/√3 is indeed a local minimum for our area function. Therefore, plug in 1/√3 into here and you'll get the output of the actual minimum area of this thing. Let's do it. All right, so a 1/√3 is, just going to plug it in, just straight up plug it in. 1 plus 1/√3 squared over 2 times 1/√3. 1 plus 1/√3 squared. There we go, make sure I did that right after all this work. I want to make sure I did that, yes. Yes, yes. Okay, now. In the numerator, we get 1 plus 1 over root 3 squared is just 1 over 3. Down here, we have that's 2 over root 3. Okay. Now over here, we get 1 plus a third. Okay. How do we want to go about doing this? Well, let's see. I'm going to bring this guy up into the numerator. So in the numerator we have 1 plus 1 over 3. This guy comes up as root 3 over 2. Like that. Yeah. 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 This thing is 1 plus 1 third. Okay, let's get some more room over here. Okay, so again, the area, the min area should be, okay, 1 plus 1 over 3 times root 3 over 2 times, now 1 plus, so that's the same thing as 3 over 3 plus 1 over 3, that's 4 thirds, right there, 4 thirds. So 4 thirds. And in fact, that's the same thing there. That's also 4 thirds, right? 4 thirds. Yeah? And 4 thirds. And we have root 3 over 2. 4 thirds. I don't think I've gone this direction before. I've normally like killed some denominators and stuff, so I hope this works out. Okay, one thing I noticed right away is, oh, and look at the way that this is set up, right? I was about to say, root 3 in there, that cancels because root 3 over 3, that's the same thing as 1 over root 3, which would be true, but it doesn't get me closer to the answer I'm looking for. So I do want to keep that root 3 in the numerator. And now, oh, I do see a good cancellation going on here. 2 and 4, those, you could divide that out. So we have 2 times root 3 times 4 on the top. On the bottom, we're left with 3 times 3. 2 times 4 is 8 times root 3. 3 times 3 is 9. And is that what we got? Lo and behold, it is. Very difficult problem. For a lot of reasons, obviously, right? You had to remember stuff from Algebra 2, like how do you deal with something that looks like this. How do you solve that? That's some Algebra 2 magic going on right there. That's probably the other big difficult part of this. But the crux of it, and what will mess you up over and over and over again, is that you're given these functions of x, and we're so used to thinking of, well, the thing that you vary is x. So we're going to call this point that I'm varying x. But they play different roles here, right? And so if you're stuck on I need to have my function as a function of x, well then you might want to go through and call this t and call this t, because otherwise you end up with the equation of your line is this, and that ain't a line. And if you just plug along with that, you're going to see like it's not going to work out well for you. So very difficult problem. I hope you guys enjoyed it. Have a good one.